Hi, my name is Philippe, and I'm glad to present to you our research about automated drywall finishing with a collaborative robot arm. First, let's talk about drywalls. So, drywalls are walls that are made from gypsum board. They're also known as drywall panel or plasterboard. They are screwed to the wooden frame of the walls, and then a compound joint, also known as plaster joint or mud joint, is applied on the seam between the board to create uniform and flat walls. So gypsum board are widely used because they're fast and easy to install. The problem is that once the compound dried, you need to finish it with either power tools or manual tools. And this is very inconvenient for workers because it produces a lot of dust. You need to work at height for certain walls, and there's a lot of physical stress, mostly on the wrist, but also on the shoulders when you need to work with your arms over them. So sanding drywall is very inconvenient. Even though drywall finishing is quite inconvenient, it's absolutely necessary to do. It makes sure that the compound is flat and that you cannot see the seams under the paints. It also smooths the compounds and remove drying anomalies. So when the compound loses moisture during drying, it's gonna shrink a bit, and this is cause a lot of problems like creases, bumps, and cracks. So, our broad objective was to design a robot that can finish the compound and help workers with this task. So we choose to use a robot arm, a collaborative robot arm with the same orbital sander used by workers, placed on a mobile platform and a vertical axis to place the robot in front of the compound and use the robot arm to sand. And our specific objective for this my paper was to determine if the robot finishes were equivalent to human finishes. So to quickly explain how the robots work, we first need to talk about the perception module. So we'd like to see where the compound is in relation to the robot. So use a RGB camera with a stereo depth in addition to UV floodlights. So we can use the UV floodlights to highlight the thin layer of paper on the gypsum board. This let us do segmentation and contours to find where in the image is the compound. And since we have also a stereo depth module, we have a point cloud with 3D convention that we associate with that image. So with the point cloud and the contours associated with them, it's quite easy to control the robot. We first need a trajectory, a zigzag trajectory to cover all of the compound in the image. And we transform those trajectory points from the environment of the camera to the robot environment. We calculate the inverse kinematic and send those joint positions to the robot via TCP server socket with Rust Industrial. And with the FANUC own force control, we can make sure to control the contact force on the wall to make sure that the orbital center at the same pressure so that the finishes is even. To measure the compound before and after the robot finish, we use a portable laser scanner. So this picture one from Creform use a reference target to make sure that we have a precise and repeatable scan of the wall. With the point cloud from the scanner, we can reorient it in the camera frame standard from the perspective of workers working on the wall. So Z toward the wall, X to the right, Y to the floor. And this let us make a depth map of the joint of some sort. So in the middle part where the compound is Z minus because it's closer to us, and in the wall part on each side it's further from us, so Z positive. So we can see the compound that is raised in the middle and the wall that are further away from us. To have a better idea of the general profile of the wall, we can use the average of y across x to get the profile of it. So here we have the left wall, here we have the right panel, and in the middle there's the compound that join the two of them. We can see that sometimes the panels are not quite aligned, but the compound make up the difference. And on the graph, we can also see the position of the targets that are slightly raised. The important part of the scanning is now to see the difference of before and after the finish. To do so, we reuse the targets that were outside of the compound to realign the scan on top of each other. So we can now take the difference in depth to create a new map of where there's more difference between. So we can see in the middle in Z positive where most of the material was removed, and we can also take the average of y across x to see first the red line that was before and the green line that was after, and the blue line that is the difference, so where we remove more material. This is also quite fun because we can see there was a creases that was removed with this method. Now that we have the depth of material removed, we can compare the workers to the robots. First, let's see our workers. So we take for each of the different joints that we measured, the depth of material removed, and we can see the average depth, the standard deviation of depth, and the 95th percentile of depth removed. This is useful because we don't want to pierce the compound. And we can see that on average, workers removed about 0.09 millimeter and at a standard deviation of 0.05. So if we compare that to the robot, we see that the robot had an average of 0.1 millimeter of material removed and a standard deviation of 0.04 millimeter removed, and also a 95th percentile that is lower than the workers. So at a quick glance, the robot seemed quite similar to the workers. So if we make a quick comparison between the robot and the worker, we can see that they have about 0.01 millimeter difference on their average and their standard deviation, and also for the 95th percentile. So this is quite a good result, but we can ask ourselves, well, how actually similar are the two of them? To make sure that the robot is similar to the workers, we can do a statistical difference test. So with a t-test, we found that there was no statistical difference between the two sample groups, but this could happen because we had a quite low number of samples. So if instead we do a power test, or should I say an inverted power test, if we assume a power of 80%, we could have detected a difference of 0.054 millimeter. This is quite interesting because the workers' standard deviation is 0.05. So in other words, if there was a difference between the robot and the worker, that difference would be smaller than the worker's own standard deviation. So this is quite a reassuring result. Conclusion, our main findings showed that the robot removed trees, bumps, and cracks, isn't likely to pierce the compound, and remove about the same amount of compound compared to workers. So using a collaborative robot to sand drywall is a promising technology. Thank you.